Hi there and welcome to this video for Senior Physics on electrostatics and electricity. In this video we're going to explore electrical potential. But first let's just recap on what we've learned in our previous lessons or tutorials so that we can fully understand what electrical potential is. Now firstly we know that we've got two types of charges. We've got negative charges and we've got positive charges. Negative charges basically have field lines which are generated, which basically is the force that would be experienced by a test charge if placed close to these charges. We know that for a negative charge, the electric field lines go on an inwards direction, and for a positive charge, they act out. As we stated, interaction of these field lines will produce a force. That force could be an attractive force, as in a positive meeting a negative, where the field lines are acting in the same direction, or it could be a repulsive force, where we've got either negative versus negative or positive versus positive, and in this case the two field lines are acting in opposite directions. The result is they interact to push them away. So basically this type of force will vary according to the size of the charges and thus according to the electric field lines. It is also directly related to the distance where we put the charge, and as a result we get this formula that we looked at earlier. F equals the proportionality constant times Q1 times Q2, all divided by the distance squared. Obviously we need to understand this if we're going to understand how two charges will interact the closer we get them together, and this was discussed earlier on. We also know that the electric field strength will basically vary according to the force and the size of a specific charge placed in that field. Hence we get the electric field strength equals the force divided by the charge, or the test charge. The electric field strength also diminishes the further away we get from a charge, which incorporates this inverse square law that we looked at with respect to force. So the further we get away from the center of the charge, the electric field lines begin to diminish, and as a result we get E equals KQ all over D squared. So in order to bring if we take a like test charge and it's brought close to another charge, the closer it gets, the greater the force of repulsion is, because what we've got is we've got many electric field lines interacting in close proximity to each other. The result of that is they want to push away, a bit like two North Pole magnets trying to interact together. Now, in order to keep it in a specific position, we have to do work on that charge. So if I've got a charge here, and I want to put another charge over here, and I want to push them together, and they're like charges, what the field lines want to do is push them apart. But I'm going to have to do work to push it into that point. So think about your north and two north poles of a magnet. If I want to put them together, I am going to have to do work in order to push it and counteract that repulsive force. Now we know that work is a form of energy, so we're going to have to put energy in to put them close together. And from this an algorithm can be set up which is similar to the algorithm for gravitational potential energy. And if you remember what we said right at the beginning when we were looking at electric field lines, that the electric fields are just like gravity. They've got radial lines and they act to actually push or pull. For electric field lines. Obviously for gravity they only have the effect of pulling, which means that when we're looking at gravity we can deal with MGH, which is the gravitational potential energy. Well, for work done in an electric field we can use a similar sort of algorithm, where we've got our mass is going to be the charge, our force, basically what generates the force, is going to be, instead of gravity, we're going to have our electric field strength, and D is going to be the distance apart, which is the H part of MGH. So from this, the work that's done to push a charge close to another charge can be calculated using Q, the charge which is being used to push against, the electric field strength, and the distance apart they happen to be. Now work will be measured in joules. So if I was then to release the force holding it in place, the result is, from the law of conservation of energy, that work should come back out. I should actually release that work. And basically, we can get that work acting in an opposite direction. Now, the release of this energy is termed voltage and can be defined as the amount of energy per coulomb of charge. Now, we can illustrate this using this diagram here. Basically, trying to put a charge close to another charge is like trying to push something uphill. If you can imagine trying to push a car up a hill, you push it up the hill, you generate a force, and you're pushing. Now, you're counteracting the force of, in this case, gravity. Gravity is trying to pull your car downwards. Now, obviously, the further up the hill you go, the more energy you're going to have to put in. Now, let's say you remove that force. What's going to happen is the car is going to roll down the hill. It's going to roll down the hill with exactly the same energy that you put in going upwards. So if you're at the bottom of the hill, you will notice all that energy, especially if you stand in front of it. Not a good idea. Well, it's the same here for charges. Basically, we've got our static charge sitting at the top of the hill, and what we're going to do is to try and push our test charge up that hill. Now remember, they're like charges. So as the distance decreases, the force that I put in actually increases. And you can notice in this diagram that just like we have contours on a map showing the steepness of a mountain on an Ordnance Survey map, you can get exactly the same with the electrical fields. The closer those lines get together, the result is more forces, the steeper I'm going to have to go in order to get these charges close together. And we find that the steepest point is going to be right at the very, very top as we're getting close to the charge. Notice that D there will be incredibly small. And this is exactly due to the electric field lines which are generated. As we get closer to that charge, the distance decreases, the electric field lines, or the density of those electric field lines, increases, which means that I'm going to be generating a huge amount of energy. So I'm going to have to put a huge amount of work in to push that test charge right up to get very, very close to my static charge. The result is I'm going to have huge amounts of electric field lines. Because they're the same charge, they're going to be wanting to shove them back, which means that the energy I put in to put it in this place is basically going to come out. Now think about it for a minute. Isn't that exactly the same as what happens in a battery? In a battery at the negative terminal, the reduction process causes electrons to be pushed to the very end of that battery. Now, a 1.5 volt battery basically means that I've put 1.5 joules of energy at one end of the battery per coulomb of charge. When I set it a circuit, those electrons will fire out with 1.5 joules of energy per coulomb. Now take a car battery, which is 12 volts. What I'm doing, I've now got a very big battery, which is putting a huge amount of electrons. They're being repelled, that they want to repel each other, but the chemical charge is pushing it in one area. It's pushing it close to each other. So it's getting higher up the slope. 1.5 volt battery would be low down the slope. A 12 volt battery will be high up the slope as it packs all those electrons together. As soon as I put it in the circuit and switch it on, those electrons will flow out as quickly as possible. So as a result, we get this release of this so-called voltage. Now basically voltage can be determined using the algorithm V equals work per coulomb. It's the amount of energy per coulomb. So remember, work is Q times E times D. So we could substitute that if we needed to. And as a result, voltage will be that work time divided by Q, where, as we say, voltage is V, work is in joules, and Q is the charge in coulombs. So as a result, as we move it from one place to the next, we actually get a potential difference. And the bottom diagram demonstrates this. If I want to move a small test charge, so that's little q, close to a big test charge, which is positive q, the result is as I move it from one place to the next, I will get a potential difference. Now, a potential difference we will look at later when we look at electricity, but basically it's the difference in energy from moving it from V1 to V2, which is a difference in distance D1 minus D2. So hence I can calculate what those changes are. So to recap, potential difference or voltage is the difference in energy as I move it from two different points as it's getting closer to a specific charge. Remember, if I release the force, pushing it close to that charge, I'm going to get that energy out. So I hope you found that useful in that explanation with respect to electrical potential. What I've now done is set up an exemplary video to show a fairly complex question of how we can solve it in an exam. Well, thank you for joining me in this electrostatics unit, and I look forward to meeting you again. Our next videos are going to be looking at electricity. So hope you've enjoyed it, and I look forward to meeting you again in our electricity unit. Bye for now.